All right, so we want to thank you guys for coming to our, I believe it's our fifth installment of the Dwayne L. Ford Lecture Series. This is again from the Andrews University Department of Chemistry and Biochemistry, where we are in our 2024 spring semester. And I think we have a lineup of about 15 speakers for this semester, I think. This afternoon, we are privileged to have a speaker, Alissa Matus. I think we met online when you were a PhD, and maybe in your senior year or so.
Yeah.
Yeah, and you were doing some really cool chemistry. She is a scientist and educator with a PhD from the University of California, Irvine. She's now assistant professor at Fullerton College, also in California. Her PhD research work focused on transition metacatalyzed transformations, one of which she will talk to us about today. For her, Professor Matus, her mentorship is mentoring is part of her reason why. Why do you want to do what you want to do? Why are you interested in teaching? Why are you interested in educating? So the why for her is mentorship. And she's particularly focused on increasing access to quality mentorship for students from historically excluded groups. She loves being in the classroom, and her free time is found with a small dog called Apple Pie. I've never heard a dog named Apple Pie. The time is yours.
All right. Thank you so much for that very kind introduction. Hello, everyone. I'm very, very thrilled to be here. I'm hopeful I can teach you a few things, get you a little bit excited about transition metals and transforming CO2. My name is Alissa Matus. I am an assistant professor of chemistry at Fullerton College in beautiful, finally sunny again, Southern California. I just graduated last spring from UC Irvine, and I have, while I have a couple of premature gray hairs to thank UC Irvine for, I also have a lot of very cool chemistry that I was able to perform while I was a graduate student. So I'm going to be talking to you about that today. But first, I have to start off and set the scene for all of the research that I'm doing or that I have done. So I'm going to show you this image. This image depicts average temperature for each year in the United States since 1895. So I want you to take a minute and kind of soak this in. You can see, oh, that's very pretty colors. For those of you who are colorblind, I apologize. But you can see that there's a really obvious gradient of color change that has occurred over time. And as time has progressed since about the 1990s, we're really only seeing average temperatures in red. So why is that? That's because our climate is changing. Okay, as global temperatures increase, we now know that a lot of those temperature changes can be attributed to global climate change. So, okay, you have absorbed this picture a little bit, and I've got you thinking about climate change hopefully a little bit. So now, since I am an educator, I'm going to have some interaction with you. So if you can get out a phone or any kind of mobile device, I'm going to ask you to participate in this Slido. This is going to make a beautiful word cloud, and I want you to answer this question. What did this warming stripes tapestry make you think of? So please take a moment. I'm going to wait for us to get at least 5 responses until we continue. So please, please interact when you're ready. Yes, the difference between each shade is not 1 degree, but instead a color is attributed to each average temperature in the United States. Global warming, it's hot. It is hot, yes, and it's only getting hotter. A quilt and concern, okay. I'll be very honest, I love to crochet and I have thought a lot about making a blanket based off of this pattern. A little bit different across the globe. That's a nice question. Facts, yes, it is supported by a measurement. So these are observations rooted in fact. Awesome. Why so hot? Yes, why? Why indeed? There are definitely cycles that we go through. And yet the trend overall over this almost 200-year record is going up. Yes, just in the United States. And the cool thing about this is that if you at any time go to showyourstripes.info, you can produce a tapestry like this, the one that we just saw, for almost any region on Earth. So you can do it for Michigan. I looked at mine from California. You can look at global warming patterns and everywhere, all over the place. But there are no places on Earth where the warming pattern does not continue to increase over time. And so we have to talk about why. We have to talk about why this is happening. And the reason why is climate change. So climate change is driven in large part by carbon dioxide concentrations in the atmosphere. Studies over many, many, many years of data collection have shown us that the atmospheric concentration of carbon dioxide is increasing not just rapidly, but it is also projected to continue to increase. And so because of that, that means that CO2 in our atmosphere is very easy to find. It is ubiquitous. It is the most abundant greenhouse gas. And greenhouse gases are who we have to thank for global warming. So with climate change comes extreme temperature. And with extreme temperature, we start to observe these phenomenon of extreme weather. So as climate change continues, weather and weather patterns all over the globe are exacerbated by the increased amount of carbon dioxide present in the atmosphere. So as global climate change occurs, we are going to see more and more instances of extreme weather. Now, it's very important to make this distinction. And when I say extreme weather, I do not just mean extremely hot weather, but I also mean extreme weather phenomena. So that includes hurricanes in tropical areas, but that also includes tornadoes, that includes large snowstorms, that includes instances of glaciers and ice melting. And these are things that we are only going to continue to see more of as time goes by. So climate change equals extreme weather. This is something that we have started to see a lot more, and it's something that we are going to continue to see. But not all hope is lost. So while this is true and it can be quite scary at times, the point of this is not to scare you, it is instead to show you one particular avenue of addressing this concern that we can take as scientists. So as technology improves, we start to have access to better and better methods of generating renewable energy. And renewable energy, particularly energy harnessed from sunlight, is something that we can really aspire to because sunlight reaches all corners of the globe almost. And because sunlight really hits every continent at least a bit, if we as a society were to rely upon sunlight for our energy needs, we could stop contributing so much to the current CO2 crisis in our atmosphere. So, as a chemist, as a research laboratory trained chemist, I had to ask myself this question. I am inspired by solar power. I'm inspired by renewable energy, and I'm super excited to be able to make connections between renewable energy and chemistry. So the question now for myself and others who have pursued this area of research is, can scientists harness the power of the sun to drive our chemistry forward? The answer is yes. Yes, we can, in an ideal world. So if we begin with our target, CO2. CO2 is what we really want to address, okay? Carbon dioxide mostly comes from pollutions from large-scale corporations that pollute the earth as they have manufacturing products, as they burn fossil fuels in order to power engines and vehicles. And CO2 can be found in the atmosphere, okay? So from there, we can use solar power to generate electricity. And there is a certain type of chemistry specifically that is driven by electricity called electrochemistry. And if you're not familiar, I want you to think of electrodes. I want you to think of a battery, the ends of a battery connected to the sun. Okay? That battery is then going to be responsible for pushing a chemical process from start to finish. So after we have harnessed this power from the sun, what do we actually want to do with it? What is the chemistry that we want to do? The chemistry that we want to do with this power is CO2 transformation. There are a lot of different terms to describe this process, but the repurposing of CO2, a greenhouse gas that's found all over the place, especially in our atmosphere, can be performed in order to achieve the production of fossil fuels, or not fossil fuels, I guess, but renewable fuels. So this image that says C1 plus, I want you to think of C as carbon, okay? My personal favorite element, even though I work with metals all the time. So carbon products that are small, that have one carbon or more, are very, very high in demand because they are used for so many different purposes as fuels themselves. They can be used for energy transport. And if we can produce fuel in this way, and even if someday we were to use that fuel to generate CO2 again, we should theoretically be able to have that go back into this cycle. So this is chemistry that is inspired by nature, by photosynthesis. Nature is the greatest chemist that there is. And photosynthesis is one of the most fascinating and powerful processes. So we know photosynthesis is something that plants do. Leaves perform photosynthesis in order to convert CO2 to something else more useful. For human beings, that really, really useful thing is oxygen. We breathe it, we need it. And similarly, if we can use CO2, which is so abundant, so ubiquitous, to produce value-added products, then we can design chemical processes that are very, very powerful. Now, the problem comes with the atmosphere and the contents in our atmosphere itself. Because when these companies pollute the atmosphere when they produce greenhouse gases as a result of their processes. Carbon dioxide is not the only thing that's in our atmosphere. There's so many other types of greenhouse gases. There are other types of gases as well that are present in the atmosphere. And if we are to do our chemistry, we need methods that will allow us to do this chemistry selectively. Okay. So look at this image for a moment and look at how many different structures you see. There are quite a few. Okay. CO2 or carbon dioxide is present here. Oxygen is present here, water is present here, hydrogen gas is present here, and there's so many other types of gases that are also present in this mixture. So if we are to perform our chemistry, we need methods of selectively moving CO2 to our reaction vessels. So this idea you can kind of think of as needing to fit CO2 through this very specific CO2 box, okay? If you think of a children's toy where the task is to match a shape with a certain shaped hole, and this is exactly the kind of principle that we want to achieve with our chemistry. We need to be able to sequester carbon dioxide, okay? So how do we do that? In real life, CO2 capture is not quite the same mechanism as having a CO2 shaped hole and then pushing it through into a box. However, CO2 capture is selective for CO2. Now, CO2 capture works very, very well. There are a lot of different methods for capturing CO2 currently. However, the problem here is that these methods are run using heat and a lot of it. So why is that a problem? The problem here is that if we rely upon CO2 methods or CO2 capture methods that are heat driven in order to then take another step and do CO2 conversion, then we are limited greatly by this efficiency because our process requires so much of an input of energy. So now we are looking for ways to get around this, okay? So keep this in the back of your mind. Now I'm going to dive a little bit more deeply into the process of CO2 conversion, okay? CO2 capture is not going away, but the part that I specifically have looked at in the past is CO2 conversion, okay? So electrochemical CO2 conversion is not new. However, it has yet to be utilized to its full, what's the word? Potential. So because of this, there are a lot of fundamental studies that have laid a good foundation for electrochemical CO2 conversion. Okay, so now I'm going to show you a catalytic cycle. We're going to walk through this. So if you've never seen a catalytic cycle before, the key word here is cycle. It should be continuous. It should repeat over and over and over again. And this is the unique property of electrochemical CO2 conversion, because we should be able to produce catalysts that will work repeatedly, okay? So at the first step, we start with a reduced metal, and I'll talk about what metals we've used in the past in a moment. So starting with a reduced metal, we're then going to add an acidic proton. This is going to come from some sort of acid source, and this is going to get our, I'll use my laser pointer, this is going to get our metal catalyst ready to then react with CO2. This CO2 reaction step, this is the actual CO2 conversion that occurs, okay? And now, once the catalyst has done this conversion, it has done this reaction, it needs to be regenerated. Otherwise, this is not a cycle. And so, in order to turn over the catalyst for another cycle to begin again, we kind of zap it with some electricity. This is the electrochemical step. This is the step that we want to be driven by sunlight, okay? So if we can harness the power of the sun to produce energy, then that energy can then be used in this cycle in order to turn our catalyst over, to regenerate our active metal complex, okay? So then what metals do we need? We need metals straight from the center of the periodic table, okay? We need transition metals. Transition metals are incredible. They have so many different properties, and a variety of them work for this purpose. So in the past, my coworkers have relied primarily on platinum and cobalt to achieve these transformations, okay? So I don't want you to think too deeply about the structure of these complexes because I really want to highlight those metal centers, okay? So platinum has done a great job of performing this exact transformation. Cobalt has also been able to perform this transformation, and in doing so, they have shown their amazing potential, excuse me, for electrochemical CO2 conversion. So now, when I started my research in this area, I thought, okay, this is excellent. And now we have to take it a step forward. We have to move this forward because we want to combine electrochemical CO2 conversion with CO2 capture. Okay, so now I'm going to introduce a new area of research. Okay, this is reactive carbon capture, or RCC for short. So reactive carbon capture is a relatively new area of chemical research, but it's very exciting. There's also a lot of grant funding here. So if any students are interested in research, I highly recommend that you look into RCC for the future, okay? So what is RCC? RCC is a combination of CO2 capture and direct CO2 conversion to value-added products. So we are talking about taking CO2, capturing it in some form, and then transforming that captured CO2 into something that we can use, okay? So in order to do this, we need a capture agent. We need something that will selectively react with CO2. So think back to this image of a child's toy where you have to fit a block into a certain shaped hole, okay? Now, we are departing from the idea of having a CO2 shaped hole, but we need something, again, that will react specifically with CO2 instead of all of the other types of gases that are in the atmosphere, okay? This is our ideal. And so to do that, we typically see amine-based capture agents. When I say amine-based, I mean nitrogen-based capture agents. So these capture agents have powerful carbon-nitrogen bonds. Amines that are also sometimes referred to as superbases, or polyamines, which contain multiple nitrogen groups, and heterocyclic carbenes, which are fascinating in their reactivity, are able to react with CO2 and generate a functional group known as a carbamate. So a carbamate is our captured CO2 substrate. This is what we want to perform our chemistry on, okay? So if we can generate these carbamates selectively with our capture agents and CO2, then we should be able to achieve selective conversion of those carbamates to our value-added products. So now, what would that look like in theory? That would look like the following. So CO2 would react with an amine. And, oh, just one moment. And after this reaction to generate a carbamate, it would then enter the electrochemical cycle that we saw previously, okay? This electrochemical cycle is nearly identical to the cycle that I just showed you, the cycle that has a lot of research precedents, okay? Now, the ticket here is this conversion step. In order to turn carbamate into a value-added product, this metal catalyst now has an uphill battle. It has a lot more of a struggle to get through. So when I say this, I am referring to metal complexes that have known CO2 reduction activity. So complexes that contain platinum, complexes that contain cobalt are metal complexes that we know can react with CO2. However, because the formation of a carbamate makes this process a little bit more challenging, we need to evaluate these metal complexes to make sure that they could function in this cycle. So captured CO2 becomes less reactive, which means that generating the products that we want can be more of a challenge. While amines are typically excellent at selectively reacting with CO2, the carbamates that are generated need to be suitable for reducing conditions. They need to be ready to react with our metal complexes, and sometimes they are not, okay? The resulting carbamates that come from a mixture of CO2 and amines contain more electron density. And one thing that is very true about most metal complexes is that those metal complexes themselves tend to have a lot of electron density around them, which means that they are less likely to interact in order to have a favorable reaction and produce our desired products. So we turn back to the literature in order to try and get around this. We know that this is a caveat. We know that this is something we have to overcome. And so we turn to this area of literature called hydrogenation. Hydrogenation techniques rely on high temperatures and pressures. However, they are very, very successful at transforming amine captured CO2 into value-added products. So in our typical setup, the setup that we want to move away from, there is a distinct CO2 capture step. After CO2 is captured, it then is concentrated for further use. That further use typically begins with some type of storage. And after storage, this is when that CO2 that has been captured actually becomes used. This is a multi-step process. And it's not a multi-step process that happens all at once. Each of these steps takes time and energy and resources. And while we do eventually end up with the products that we desire, because there are so many steps in order to get here, we need to be able to get around them. Ideally, we want to do this in one go. So that is the process of RCC, of reactive carbon capture. Now, reactive carbon capture can be done with high temperatures and pressures. It can be done in one go all the way across to get to our value-added products. But what we really want to do is combine RCC with electrochemistry so that we don't have to rely on these high temperatures and pressures, because those are always going to limit our efficiency. Now, a little bit more about hydrogenation, okay? Hydrogenation literature is all over the place. This is a well-studied field. And this is why it's so exciting to be able to combine this known chemistry with all of the potential that comes from electrochemistry. So in hydrogenation chemistry, CO2 capture is the generating step for carbamate. This carbamate then reacts one time with a catalyst to generate formate. This can be stopped here, or it can be pushed even further to generate formamide and then methanol. And I'll tell you something about methanol, okay? Methanol is a C1 product, and it is exceptionally in high demand. It is very electron dense. It is dense in its ability to hold onto power in the form of electrons, in the form of chemical bonds. And because it is so dense, and it is much easier to transport than carbon dioxide by itself, we really, really want to find ways to achieve methanol production. Okay, so this is one of our targets. Now, formate, which is the complex generated in the middle, this is also one of our targets because this is one of the common targets from CO2 conversion without carbon capture. We know that we can make formate from CO2, but now if we combine CO2 conversion that we know how to do with CO2 capture, we should be able to push it forward all the way from formate to methanol. And this is what is really exciting. So in order to do this, you see these abbreviations RU. If you've ever seen the periodic table, you probably are aware that Ru is short for ruthenium. Ruthenium, my favorite metal. Now, ruthenium is a particularly powerful metal because it can be involved in a number of chemical transformations. Now, the one that I care about is carbamate reduction, okay? So, selectivity for production of formate and methanol in hydrogenation is very high. And it's all thanks so far to these ruthenium catalysts that are called Ru-macho. Okay. Now it is called Ru-macho because the ligand system, these groups that are hanging around ruthenium, kind of look like a bodybuilder squeezing the ruthenium. That's where that macho name came from. Okay. Very exciting. So in particular, these Ru-macho catalysts have shown incredible turnover for methanol production. And if we think back to our catalytic cycle, the word turnover means essentially recyclability of a catalyst. Okay, so if we have a really high turnover, that means that we can use these catalysts over and over and over again. So these catalysts are of great interest to us. Now, there is an intermediate that has been proposed in the literature time and time again, and it is this complex here. This is a dihydride. There are two hydride groups coming off of ruthenium, and while it has been proposed time and time again, there have yet to be definitive structural evidence that this complex exists during CO2 conversion or during carbamate conversion. So recent work in my previous research group showed that a cobalt hydrogenation catalyst could be repurposed as an electrocatalyst for CO2 reduction. So this cobalt complex is also known to perform hydrogenation chemistry. And the thought behind my project was that if this cobalt complex can be plucked from hydrogenation chemistry and utilized for electrochemical conversion of captured CO2, then can I do the same thing with Ru-macho? Can I do the same thing with these carbamate substrates? So I began my research project by focusing on the generation of formate, okay? So in a perfect world, if you mix carbon dioxide and a metal hydride complex, okay, abbreviated as MH, you're going to see that a bit, you can generate formate and then have a form of metal that could be regenerated into a metal hydride, in part using electrochemistry. So if this can occur catalytically, it should be able to occur stoichiometrically. So the difference between catalysis and stoichiometric chemistry, that stoichiometric chemistry occurs in a one-to-one fashion. So these metal complexes are used in an equivalent amount to the substrate. And that's where I began. I ran a bunch of stoichiometric experiments because I really, really wanted to see if this commercially available carbamate called ammonium carbamate could be transformed into formate using a metal hydride. So I asked this question and the answer was not exactly, although sometimes yes. So really, it's complicated. But all good chemistry is complicated in a little bit. So I was initially able to observe some formate production using these complexes. One is a rhodium complex. The other is this platinum complex that we've seen before because my group had used it a lot for electrochemical CO2 production. However, the formate production itself was very, very limited. Why? I'm not sure. But one of my theories is that the solubility of ammonium carbamate in my solvent was just too poor to allow for adequate conversion to formate. So I was able to observe this using NMR. However, I wanted to see if I could push this a little bit forward. So I switched to a solvent that I knew would allow me to solubilize ammonium carbamate. And unfortunately, it still didn't quite work as I had expected because now I saw the production of hydrogen, and the production of hydrogen gas after the reaction of a metal hydride and a protonated amine is a side reaction. So I saw this new reactivity. I saw the generation of formate, but then I also saw the side reaction that I know is going to be competing with the reaction that I actually want. Okay, so I had to kind of breeze past that. While ammonium carbamate is cheap and it is commercially available, that solubility proved to be a really, really big challenge for this chemistry. So I returned to this platinum complex. I tried to track over time because I thought maybe this process is just slow, the production of formate. However, I saw that about the maximum yield that I could achieve of formate production was just over 7%, even after 24 hours. So I turned to this complex, this rhodium complex, and I synthesized this, and I was able to combine this with DMSO, the solvent that I chose to solubilize my substrate. And I saw that the catalyst itself decomposed. So I felt myself running into a corner, but I returned to acetonitrile, the solvent that I had some initial success with. And I did again see the generation of formate after the mixture of this rhodium complex and ammonium carbamate. I didn't see any H2. However, I still didn't see an increased amount of formate being produced. So I had to look away from these complexes and turn to Rue Macho, the known hydrogenation catalyst. I know that Rue Macho is capable of converting carbamates to formate. So if I were able to access this dihydride, I should be able to perform these stoichiometric reactions. So again, this dihydride had never before been isolated or shown in the literature. However, proposed mechanisms for carbamate production were reliant on the generation of this catalytic intermediate. And so the aim that I turned to then was to access this dihydride. And of course, as most things do, it turned into a very lofty goal. It was very challenging. But I decided to start with this form of the Rue Macho complex, use a chemical reductant, and try and isolate this proposed dihydride. So I took a few routes. The first route that I tried was with sodium borohydride. This is a known chemical reductant. It is quite powerful. However, this borane is known to coordinate with ruthenium. So I knew I wouldn't be able to use this and actually access this dihydride without some coordination of boron. And I wanted to avoid that. So instead, I turned to a reductant called superhydride, or lithium triethyl borohydride, which is not known to lead to borane coordination to ruthenium. And this has been used in the past to similarly generate ruthenium dihydrides with different ligand systems. And so I thought this would be perfect. And I was kind of right. So the dihydride that I was able to access using lithium triethyl borohydride, I later saw was able to perform the carbamate reduction step. And this is exciting because I know, not just from literature, but also from experience, that this starting form of rumacho, unless it is transformed first to the dihydride, this version of rumacho, the monohydride, does not have any CO2 reduction activity. It does not have any carbamate reduction activity. So upon the generation of this species that I was later able to characterize quite a bit, I was able to observe that I could access this dihydride. So that was very exciting. I was also able to access the dihydride using sodium hydride. Now, usually sodium hydride performs as a base. However, it has been shown in the past to generate metal hydrides under certain conditions. So I ran the same reduction and I saw that the products shared hydride peaks via NMR. So this was really encouraging to me. I was able to take these two separate methods and make more dihydride. So something that is interesting about this, I have a lot of NMR data about these dihydride complexes that result after reduction of the ruthenium monohydride, a lot. And after comparison, I noticed that sometimes there were a lack of defined hydride peaks following superhydride reduction. And remember, superhydride has lithium in it. After some really long-winded attempts to isolate a complex following superhydride reduction, I was able to get out this really interesting crystal structure where instead of just having one ruthenium dihydride, I saw two bridged dihydride complexes coordinated through these common lithium atoms, presumably sticking around from the initial reduction step. So one of the reasons I decided to go forward with sodium hydride as a reductant instead is because sodium does not have this Lewis acidic effect with metal hydride complexes. So of note is these fully deprotonated nitrogen atoms in the ligand backbone. So I was able to see these dihydride complexes. However, they really weren't what I had hoped to isolate. So instead of staying here, I decided to go forward with a complex reduced by sodium hydride. And I was finally able to isolate this cis dihydride ruthenium complex. And it was really an exciting day for me. I've been trying for a long time. And it looks really nice. So I was very excited to be able to see this. But then the true test was to isolate this dihydride and try and generate formate. And so that's what I did. I isolated this dihydride, especially after the characterization with crystal structures, and I subjected it to an atmosphere of CO2 just to see if I could do a simple conversion of CO2. And I could do it. I did it. It made formate. I was so excited. And while I did see coordination of that formate in the form of a formulated ruthenium complex, still that formate generation was so exciting to see. So after this formate generation, I had to look back at my commercially available carbamate substrates because I really, really wanted to nail down the ability of this dihydride to convert a carbamate to formate. And so instead of using ammonium carbamate, I instead used dimethyl ammonium dimethyl carbamate, a slightly more stable and much more soluble commercially available carbamate. I then added an excess of this carbamate to my ruthenium dihydride complex. And what did I observe? I observed the production of formates. I was so excited at this point because not only was this formate produced from my ruthenium dihydride compound, but it was also not bound to the ruthenium itself. So I found that absolutely fascinating. Now, at the same time, I did also see H2. I saw some hydrogen production. So I went to study this a little bit further. I wanted to make sure what I was seeing was actually this ruthenium-2 complex. So I really needed to double check the oxidation state of that ruthenium and see if it changed. And really the major peak that I was able to see was in fact a ruthenium-2 species. So this was a really exciting day. And now, because I really want to make sure that I make time for questions, I'm going to wrap up a little bit quickly. But all in all, really exciting to see this reactivity. Now, I'm going to give you some of my major conclusions. These are conclusions that my coworkers, my previous coworkers, are now carrying forward in some exciting chemistry of their own. But the concluding statements from this ruthenium dihydride complex I was able to isolate and characterize, but that formate was able to be produced using this dihydride from CO2 and dimethyl ammonium dimethyl carbamate. This is the first time an isolated rumacho dihydride has been isolated and demonstrated CO2 reduction activity. Future electrochemical studies will have to pay a lot of close attention to the selectivity, however, of this complex. Now, if you think back to the slide I just showed you a moment ago, I told you that I made some hydrogen, and hydrogen is a side product. It is the product of a side reaction that we don't want. So if this is going to work as an electrocatalyst, then we must pay attention to the selectivity of this complex to react with captured CO2 or CO2 over the production of hydrogen, okay? And last but not least, one of the crucial key steps in getting a complex ready to react with CO2 and carbamate in an electrochemical cycle is the acid that is used to generate a metal hydride. So suitable acids are going to need to be screened in order to identify one that is right for electrochemical production of this dihydride complex. Now, I want to leave you with a final note because I know that we started out on a semi-grim topic of climate change. However, my note is that hope is a natural resource, just like sunlight. And there is so much hope for our environment, for the state of climate change. And I want you all to, if you have a chance, go to this article written by Greenpeace and see that there is so much hope, not just in the chemical sector, not just in the research sector, but in the human sector. Just by you being here today and listening to me talk to you a little bit about this form of chemistry that will hopefully have an impact on sustainability, we are making a lot of changes. The key is education. This is our very first step. It has to be. So climate change is far from being hopeless, but there's a lot of work to be done. So while I have gone on to a new position as an assistant professor, and I'm not directly involved in these research activities anymore. I can tell you who is, my previous coworkers and collaborators. These are amazing, profound scientists who are really paving the way forward for more RCC technology, for more carbamate and CO2 reduction, and for the combination of CO2 capture and CO2 conversion to make new RCC cycles. So what kind of scientists do this kind of work? Chemists are responsible. We also have engineers, environmental scientists, ecologists are part of this team, even computer scientists, mathematicians, and of course, biologists. So please do not limit yourself based on what type of research you're interested in. You could absolutely be involved in this. Okay, so my very final slide is just more acknowledgements for my funding sources. Of course, the institutions I'm at now, and a call to action. Students, connect with me on LinkedIn if you're interested in talking about sustainable research. Educators who are watching now, please consider incorporating some aspect of climate justice into your courses. If you follow this QR code, you will be taken to a website with many different modules where this has already been thought out. So please consider incorporating this into your courses. And of course, if you'd like to connect with me, please feel free to send me an email. I'm happy to talk at any time, especially about research that I think is cool. And finally, thank you for your time. I'm so glad that I was able to be here, and I would love to take any questions.
Okay. Okay, question, Ian. I saw that your reaction was 12 hours and that ruthenium was the cheapest transition metal. I had a question about that too. What does the forward reaction rate look like? That's the first of several questions from Ian.
Ian, oh, thank you for your questions, Ian. Are you a student?
Yes, he is.
Excellent. Okay,
Junior?
so
Junior.
awesome. Okay, so let me try and answer in order. So let's see. Forward reaction rate really depends on the substrate. It really depends on the conditions as well. So for hydrogenation, one of the reasons why the time period of these reactions are typically a lot longer is because they're doing this in a batch. They're doing this process with a lot of material. For myself, for my stoichiometric reactions, the time periods that I used were relatively long, 12 hours, so that I could track reaction progress. I was hoping to see more conversion than I did. However, that rate of reaction seems to be pretty quickly. There may be something impeding the catalyst from reacting continuously over time or reacting with all of the substrate. And that's definitely something that's being looked into now. So that 12-hour time frame is really to give me time to track the progress. So let's see, in your mechanism, oh yes.
Before you
Go
go
ahead.
into the mechanism, is ruthenium really cheap?
It is actually quite cheap. It depends always on global markets. Right now, I want to say rhodium is quite expensive because it's found in catalytic converters. And that's one of the reasons why there's a catalytic converter theft crisis because rhodium is so high in demand. So really, it's just about what the markets are looking for. While it is true that ruthenium is not as abundant as other metals, depending on demand and depending on extraction technique, ruthenium can actually be quite affordable.
Okay. So the next part is in your mechanism, how hard is it to push it towards formate?
It's not hard. That CO2 conversion step is actually quite fast and happens rapidly. So in previous work with platinum complexes, with cobalt complexes that my research group used, that CO2 conversion step was always quite quick. The energetic barrier for that conversion is low. Whereas for the conversion of a carbamate, it is much, much higher. which is why we have to use more powerful complexes in order to perform that conversion.
Okay. So yeah, that's connected to the question about the expense. Is the whole process profitable? Yeah,
Okay, so if
is
it
the whole
were
process,
profitable, can make
yeah,
cell formate. Well, that's the hope. So
yeah,
I'll tell you right now, the process is quite expensive. And it is expensive because of material costs. It is expensive because of equipment costs. It is expensive because of time and energy that is required for us to do this, I would call kind of foundational research. And I think that one of the best parts of being in a large collaboration, not just with chemists, but also with engineers, is that the cost effectiveness is something that is being addressed actively by these engineers who are much more familiar with the key aspects of the process it will take to take these transformations to scale. And
mhm.
so while I am not responsible for that, and while I was truthfully not thinking about that because my work focused on the transformation, it is actually being addressed by these projects. So it is definitely something that we're thinking about as a whole.
Okay. Then Suvan, another junior, right? Junior chemistry major. How much of the analysis of metal catalyst effectiveness was carried out using cyclic voltammetry?
Ooh, this is a great question. A good amount. So something that I did not talk about today was the electrochemistry that I did with Rumacho. Rumacho, like the substrate ammonium carbamate, has a lot of solubility issues. So there are really idealized solvents that we like to use for electrochemistry, particularly acetonitrile. And acetonitrile doesn't get along very well with Rumacho, which means that my studies were a little bit more challenging. But I will say that I was able to characterize these a bit with some cyclic voltammetry. The results I showed you today do not incorporate those really at all because they're so much more preliminary, but cyclic voltammetry is constantly being used. And in previous work that the group was involved in before I started, cyclic voltammetry is always relied upon to study reaction rate of platinum complexes particularly, but also cobalt complexes, because we can usually see using CV a good potential that we can run our really long electrolysis experiments at. So CV is always being used, even if it doesn't show up.
So it was kind of interesting to me to actually see hydrogen gas on
Yeah.
NMR spectra.
Mhm.
As an organic chemist, I don't see that. So
It's
what show us that NMR again? It was
yeah,
a
of course.
four
So
point
let's
something.
see. Mhm. Okay, here's one.
Yeah, so it's about 4.5,
Mhm.
4.5 ppm.
Mhm.
Yeah, I just found that fascinating. So you captured it maybe in some specialized tube or something, and then took it to the NMR.
This is in a regular NMR tube. I
Okay.
think sometimes I was using J Young tubes specifically. However, more often than not, this peak showed up. And to me, that's an indication that if I can actually detect that peak, there is a significant amount of H2 being produced,
Right.
which is an issue, of course.
Yeah.
So one of the things that we observe that has been the case for all of the complexes that we've used for some reason is that using acetonitrile for these reactions will essentially shut down HER or hydrogen evolution completely. And we are not entirely sure why. So the instances where I saw um, hydrogen being produced were always in solvents that were not acetonitrile. Now, if we were to perform electrochemical conversions with this complex, we would like to do it in some kind of acetonitrile or maybe benzonitrile solvent, because that's just standard for most electrochemical experiments. However, because of solubility, as I ran these stoichiometric experiments, I always prioritize the solubility of my complex and my substrate first.
Yeah. All right, well, thank you. Oh, one more question?
Yes, I was wondering, when you're doing the electrochemical reactions, you get more energy out of it.
When you're doing the electrochemistry,
Hmm.
was there more energy in than out? Is that? Yeah,
In then out. Okay, more energy in than out. I think this comes down to a question about efficiency, if I'm interpreting this correctly.
yeah, yeah.
Okay. I don't have a great answer for that, and I'll tell you why. The majority of my electrochemical experiments with these systems were for the purposes of characterization and not a measure of efficiency. Because I really turned my focus at the end to isolating and identifying the rumacho dihydride, while I was able to use it for some electrochemical experiments, those, like I said, were really focused on characterization instead of a look at efficiency. So I don't have much to say to that. However, I can say that in the past, the reaction efficiency is almost always dictated by the turnover number for the catalyst. And as we've seen in hydrogenation literature, the rumacho catalyst itself is very, very stable. It is very good at turning over. So my hope is that for future electrolysis experiments that will be run by my coworkers, we'll see a good amount of efficiency because the catalyst itself is ready and willing to be turned over electrochemically. That's my hope.
Okay. All right, well, we want to thank you again for giving us some insight into repurposing CO2 and the chemistry behind it, using transition metal catalysts. Thank you very much and continued success in your research and in your work.
Thank you so much.
All right, take
Thank
care.
you for having me.
Not a problem. Thank you for accepting.
Of course.
All right, take care.
Thank you so much. You too.
All right, bye-bye.
Bye-bye.